כן, זה הרבה פחות מוכן. גם הרבה יותר קצר.
נחכה עוד איזה דקה או שתיים. Shall we wait another couple of minutes? What's the situation in the seminar room?
I mean, a bunch of people arrived, but
Shall we wait another couple of minutes?
yeah, I think we should.
Okay.
They still don't show up anymore.
Oh, no. So what? It takes a little bit of time. Okay,
And the Wednesday ones are on also? Or?
they're not up there quite yet. Yeah, I uploaded them all.
No,
as
it's
a
just
bulk.
because I was.
Yeah, definitely people are still arriving, so we'll wait another couple of minutes. Okay, shall we start? So hello everyone, welcome to this new day of the meeting. We shall start with Zlil Sela from the Hebrew University, who will speak on the growth ordinal of hyperbolic and other groups.
Thank you very much, and I'm really glad to speak at this conference. Well, Udi was my colleague, was our colleague for quite a few years, and actually several people left us during the, I don't know, last 10 or 20 years, but I think the fact that Udi left was at least for me, most painful, I would say. Okay, but anyway, I'm very, very glad to speak at this conference, and I chose a topic that is not exactly logic, although it's to speak about ordinal, so there's some set theory inside. But I should say that, well, it's indirectly, that's it, it's indirectly related to logic. Actually, when I worked on the first order theory of a free group, I was hoping that, you know, eventually people will do things in the spirit of Udi. That means that logic will be used to prove results in groups. Somehow it didn't happen so far, but somehow in recent years, occasionally or not occasionally, you know, on purpose or not, there were several projects that I was involved in that that used the techniques, not the results, not the logic results, but the techniques that were used in order to study the first order theory of free groups to prove results in group theory, partly to show people in group theory that you know that these techniques should be very useful even with no connection to logic. And from the work that I'm going to talk about, I also learned quite a bit about notions that I defined before for the purposes of studying the first order theory. But it has to do only with a very basic object. So with varieties, with the coordinate groups of these varieties, which are limit groups. And you see, it answers, in particular, it answers a basic question that that was asked by De La Hart, but I think there should be a lot of interest, and it raises many questions that couldn't be asked before. Okay, so what I'll talk about is growth, and actually Udi was connected to this subject again, directly or indirectly before, because Udi worked a lot around the around at least things that appear in Gromov's famous paper on famous work on groups of polynomial growth. What I'll talk about here is somehow complementary. I'll talk only about groups that have exponential growth, and all the questions will be about them. Also, apparently, not much was done in a sense on groups with exponential growth, and there's a lot to ask, and also, of course, to try and prove. Okay. I should say this work is joint with Koji Fujiwara, who's a group theorist, originally differential geometer from Kyoto in Japan. Okay, so I said we'll talk about growth of groups. This is essentially this is a combinatorial definition to do with counting. So we have a group. We will talk about finitely generated groups. So usually with the group there will be specified a finite set of generators, and at least for me, then one can think about the Cayley graph, and we can think about the ball of radius n in this Cayley graph. Okay, this is just all the words, all the elements that can be presented by words of length bounded by n, and we count how many elements are there in this ball. Notice that it doesn't depend only on the group, but also on the set of generators. Okay, as I said, so far there's no connection with with anything that has to do with logic or with varieties, but you'll see that surprisingly, this is somehow, for me, this will be the main tool to study these things. Okay, so this is some history. I'm sorry, my screen here is, I guess maybe I'll make it. Yeah, so you can see some of it. Okay, so so this is some results from it has well, relatively long history of at least 50 years studying of growth in groups. So some results are rather elementary. For example, the fact that abelian groups, it's all finitely generated. Okay, have polynomial growth. In fact, here it doesn't depend on the number of generators and the set of generators. It's always polynomial of certain degree. Only the coefficient will change. The important groups has also polynomial growth. It's not that much different. This was a work of Bass from, I'm not sure, the end of the 60s or the beginning of the 70s. And before that, Milnor and Wolf showed independently that solvable groups, finitely generated always, have either polynomial or exponential growth. Then there's a very famous and very useful for many purposes Tietz alternative that says that for a linear group, we have a finitely generated group, it's either virtually solvable, so then we can use Milnor and Wolf to study growth, or it has a non-abelian free subgroup inside, and then the growth is exponential. And probably the most, the really diamond of this subject, the breakthrough is due to Gromov from 1980 or 81. And Gromov showed the opposite, which is, looked very, very difficult. This was open for a while. That if a finite general group has polynomial growth, if you assume something about the growth, then the group is virtually nilpotent. And then Bass can compute exactly what the growth is. Then there was the question, there was a lot of work since Gromov about groups with intermediate growth. So these are groups that the growth is between exponential and polynomial, super polynomial but sub-exponential. And the first was Grigorov group, and now there are uncountably many examples, and there's a lot of work on these groups, random walks on them, boundaries of them, whatever. But I'm not going to speak about this at all. As I said, what I will be talking about in this talk will always be groups with exponential groups. So it's somehow complementary to what Gromov did, and also it doesn't touch Grigorchuk and others who work on intermediate growth. Okay, but groups will not always be linear. Okay, so we'll talk about groups with exponential growth. And if it's exponential, if we know that the group is exponential, of course, it doesn't matter what the generating set, it's a finite generating set, okay? So it doesn't matter what the generating set is, the growth will always be exponential, but the base of the exponent depends on the generating set, and this is the whole point. Okay, if we change, so we define the growth with respect to a fixed generating set to be this limit, okay, the nth root of the number of elements in the ball in the Kelly graph with respect to this generating set. And this again, it depends on the generating set. And if the growth is exponential, it's not difficult to see that by enlarging this set, for example, we can take, okay, in the Kelly graph, these were the elements in ball of radius 1, but if we'll go to a ball, we take all the elements in a ball of radius 20, because we enlarge the number of generators, then the growth will be what is the growth that was before to the power 20. And we start with something which is bigger than 1, so we can get to a sequence of numbers that easily goes to infinity. Okay, so this is, in general, this is for groups of exponential growth, this is always an infinite set. And we define this is an invariant of the group, which is the infimum over all the growth rate. Now, the group is assumed to be of exponential growth. So for each particular generating set, the growth, what I denote here by EGS, is bigger than 1. And there was a question, maybe of Gromov, whether every group has uniform exponential growth. Namely, is it true that for every group of exponential growth, this E of G, which is the infimum, has to be greater than 1 as well? And John Wilson constructed, I don't remember exactly when, but more than 10 years ago, he constructed a group that does not have uniform exponential growth. It's still finitely generated, but not finitely presented, but it's not that important now. Okay, so it means that this infimum is not always obtained. Okay, so in the group that Wilson constructed, the infimum is even 1. And for a group with exponential growth, it cannot be that the finite generating set, okay, this is the group has exponential growth. It cannot be that the finite generating set will give exponent 1. And on the other hand, there are groups that have uniform exponential growth. This means that for any, or if you want, this means that the infimum will be bigger than 1. An example for that are hyperbolic groups. It's not very difficult. This was done by Kubi, a student of Delzant, I think. And for linear groups, it's more difficult. This was done by Eskin, Moses, and O, and they did it by showing that that for any generating set that one picks for a linear group, after a bounded time, at uniformly bounded time, we will get a free semigroup, and this is enough, of course, to get uniform exponential growth, because a free semigroup and 2 generators already have growth, which is whatever 2 to the base will be 2, and what's important is for how long does it take to get to a free semigroup, and if we know that this is uniform, then the group has a uniform exponential growth. Then there were other works like Bouya and Tzachi Gelander show that it's true only for not only for free semigroup but also for free groups. So they make the Tietz alternative actually effective. But okay, I'm not going to. It will not be relevant for the talk today. Okay, so this is a question that was asked more than 20 years ago. It's actually in the book of De La Harpe, and he had a reason for that. Actually, Anna Erschler pointed out this question to me also almost 20 years ago. For hyperbolic groups, and it's not, if you don't know what hyperbolic group here is, it doesn't matter. Just think that a random group in any reasonable model, random finitely presented group, will be hyperbolic. That's enough. I don't need now to use the properties of this group. It's also true for many other groups, but of course not for every group, not for any finitely presented group or whatever. There are groups for which it's not true, but say of groups with density 1, they will be hyperbolic, and everything here will apply. And so far, as I said, people have generalized that. So what De La Harpe asks is whether the set has a minimum. So you see, before we talked about infimum. So the question was whether the infimum is obtained. There's some generating set that will give the minimum. Wilson example shows that for finitely generated group in general, this is not true. But we asked that, he asked that about hyperbolic groups, and we said one can ask about other groups. And he had a reason. And all this appears in his book. He has a book on something like, it's called Topics in Geometric Group Theory, somewhere from the 90s, I think, at the end of the 90s. And okay, so I'll just explain his De La Have motivation. So suppose that the group has a minimum. And what he argues is that in that case, the group has to be Hopf. That means a group is called Hopf if every epimorphism is actually an automorphism. So every epimorphism has a trivial kernel. Okay, so again, we assume that the group has a minimum, and we look at the proper epimorphism. So suppose there was an epimorphism with a non-trivial kernel. So there is a result by, actually this result was after he asked that, but anyway, he conjectured that either. So there is a result by Arjancheva and Lisenok that if we have a proper epimorphism between two groups, and these two groups are both hyperbolic, then always the growth of the quotient is bounded by the growth of the source. But for hyperbolic groups, if the epimorphism has kernel, I should say the kernel need not be finite, is assumed not to be finite, then it's true that the growth of the quotient is strictly smaller than the growth of the source. And okay, now suppose that there is a minimum. So we take G with this with the generating set for which the minimum is obtained, and okay, so the image of these generators will have, by this result of Arjancheva and Lisenok, will have strictly smaller growth rate than the growth of the original group. But this is impossible because the original growth rate was minimal. You see, this is a way to use the fact that you have a solution to some extremal problem, to some variation problem, in order to deduce some in this case some algebraic property of the group, which is otherwise difficult to get. I should say that De La Have actually asked this question. I proved this Hopf property before the book for groups that are torsion free, and somehow I thought that this would be an approach to prove it with torsion. But of course, people before that prove it with torsion by just generalizing the argument from the torsion-free case. But anyway, this is just a motivation for them for looking at that. Anyway, it will be interesting by itself. Just the question of a minimum or generalization of generalization of the question that we will just go to. Okay, so we will not look only at the minimal growth, but given a group here denoted by gamma, okay, in a hyperbolic group, we look at all the finite generating sets of the group. And okay, so for each generating set, we get the growth, and this will be a countable set. As I already explained, this set is not bounded. Okay, it goes to infinity. There is an infimum for this set which is bigger than 1, but the question is, what can we say about the structure of this set, in particular whether it has a minimum or not? And somewhat as analogy, doesn't have direct. There's no way to translate anything from this to what we did, but still it's a good analogy. So this is a very famous theorem of Jorgensen and Thurston. In fact, Gromov gave a Bourbaki seminar in 1979 or something like this on the work of Thurston, Jorgensen and Thurston, and somehow he concentrated on this theorem. So if you want, you can look at Gromov's Bourbaki seminar, and he even asked questions that, to the best of my knowledge, are still open, and we have analogous questions now for our work, analogous to Gromov's questions. Okay, but what they proved, what Jorgensen and Thurston proved, using completely different techniques, that if we look at hyperbolic 3 manifolds now, there are infinitely many of them. What they showed that the set of volumes is well ordered. Okay, I will not talk now about the proof. The proof is not long and not difficult, but there is some fact that needs to be proved. A very nice result of them. using that it's possible to prove that, and this fact was afterwards important for many other things. And they also proved that the ordinal of the set of volumes, I should have written here omega 0 to omega 0. Omega 0 is the first countable ordinal. Okay, so that's what they proved. And they also proved that every real number can be the volume of it was finitely many hyperbolic 3 manifolds. So this is a classical theorem from the second half of the 70s by Jorgensen and Thurston. And in some sense, as I said, this is as analogy, this is a motivation for what we are going to show. So the first thing is that, okay, this is the first theorem that we prove, is that this set, okay, the set of all possible growth of a hyperbolic group with respect to all its finite generating set, it's a well-ordered set. And okay, this is somewhat analogous to the volumes of hyperbolic 3 manifolds. And also the finiteness is true. I'll get to the ordinal in a slide or two. Every real number can be the rate of growth of at most finitely many generating sets, but we have to define an equivalence relation on generating set, because if we move from one to another by automorphism, of course the growth will be the same. But if we identify such generating set, okay, that one can move by automorphism from one to another, then there are only finitely many generating sets again. Finitely many classes or equivalence classes of generating set for which the growth is the same. This is precisely the analog of what Jorgensen and Thurston proved for volumes of hyperbolic 3 manifolds. Yeah, this is, okay, I don't know if I want to get into that now, but this is a question that Gromov asked. In the case of volumes of manifolds, it's, see, we get finiteness, or Jorgensen and Thurston prove finiteness, namely, they show that that each volume can be the volume of finitely many hyperbolic 3 manifolds. And he asked, but there's a simple trick. I'm not getting to that now. That one can show that that it cannot be bounded. It's finite but not bounded. And he asked whether if you bound the volume of the manifolds, whether then it's bounded. To the best of my knowledge, this question of Gromov is still open. And also here, one can ask the similar question, whether I call it here locally bounded. So it means that if we bound the growth, whether one can replace the finiteness in our theorem with actually boundedness. And I don't know the answer. This is really open. Okay, of course, we proved it's well ordered. Therefore, in particular, it has minimum, because any subset has a minimum. This will be important in the future, and for the rest of the talk. It's well ordered, so we can associate with this set an ordinal. Okay, so this is the ordinal of the set of all possible growth. Okay, this is really invariant of the group, the set of all possible growth with respect to all finite set of generators. This is an invariant of the group now. Okay, and therefore this ordinal is an invariant of the group as well. And what we showed is that we showed that the ordinal is at least omega 0 to omega 0. Okay, in the case of the theorem of Jorgensen and Thurston, it was equal. And the problem that we cannot prove, we couldn't prove that it's equal. Okay, we can prove it only for a special family. So if the hyperbolic group is also a limit group, or actually this is true for limit groups in general, that there is also equality here. So we can also prove an upper bound, which is omega 0 to omega 0. And the reason that we couldn't prove it in general, but only for a subfamily. But this subfamily includes free and surface groups, and even for free group, I don't see any other way to approach these things. So the reason that we could prove it, I'll get to that maybe in a slide or two. But the reason is that okay, some property of varieties. Actually, I asked this question 20 years ago, and it was answered by Lars Lauder, who's now in University College in London. so it was answered for limit groups over free group, but not for general hyperbolic groups or limit groups over hyperbolic groups. So we need his work, very nice work, that he showed that varieties over free groups have a cruel dimension. And when we know that there is a cruel dimension, then one can prove the upper bound and get this result. Here is a nice application of the fact that we know that the ordinal is omega 0 to omega 0, say for free group. Okay, it's true in more generality. It's true for a whole family, but say for a free group, you see the ordinal of the whole set is omega 0 to omega 0. But if we fix a generating set, then this generating set will have a certain growth. Okay, the growth of the group with respect to this generating set, it's some real number, and we can look at the prefix of the set of growth up to this number. So the ordinal of this prefix, because it has to be strictly smaller than omega 0 to omega 0, it's some polynomial in omega 0. And it means that what we get here is for any generating set, we get an invariant which is a polynomial in omega 0. And okay, it doesn't separate completely between generating set, but only finitely many of them can get the same polynomial. Okay, and practically nothing known about this polynomial, except that we know what generating set, just for a free group, for surface group, even this is not known. Just for a free group, we know what generating set get the value 1, the polynomial 1, which is just a free basis. Okay, this is it's not difficult to see that this gives the minimum in the case of a free group. But in a surface group, for example, it wasn't known even before that there is a minimum, and we don't know what the minimum is. Anyway, on this polynomial, it's new, but nothing is known about that.
It's Zlil, can I ask a question? Maybe I misunderstood earlier, or else do you have two finiteness statements or one? Before I thought you were saying, which I found absolutely amazing, that knowing the real number, just the base of the exponential growth, determines the elements up to automorphism, up to finitely many possibilities.
I said that there are finite. No. There are finitely many classes.
Yes. Yes. And now you said it for the polynomial, which is a different thing.
No. You see, okay. Look, the invariant is polynomial. What I compute. Well, I don't. Anyway, this is a generating set. There is a growth of the group with respect to this generating set. This gives me a number, right? A real number.
Yes.
So you look at the set of growth of the group up to this number. All the real numbers that are rates of growth of some generating set up to this number. This is a prefix of the set. This prefix of the set is well ordered.
I see.
It has an ordinal. And the ordinal is a polynomial in omega 0 because it's smaller than omega 0 to omega 0. This is the polynomial.
Yes. And this determines all, yeah.
This it doesn't determine the generating set, but there are only finitely many generating sets that will have the same polynomial.
So that's a different finiteness statement.
No, it's not a different finiteness statement.
No.
Because different prefixes will have different ordinals.
Okay. Well, it's not clear to me why you have only finitely many up to conjugation for, well, neither one is clear to me. To me, it seems like two statements, but maybe one of them is obvious. Okay, keep going.
Okay, I will.
Right, it's not a linear ordering, so you might.
It's well ordered. No, it's not. Yeah, but finitely many classes go to a point. That's all.
Yeah, so it's.
I do use linear ordering, the well ordering of the real numbers.
Okay. So you know not. I see. So knowing the prefix means also knowing the real numbers attached, not only the order type of that.
Okay, Udi, I can't hear you for some reason.
Okay, sorry. No, I think I'm beginning to understand. Okay, thanks very much.
Okay, yeah, I don't know. Okay, I wanted to get to other results, but this, okay, let me, I don't know now to go over the sketch of the proof. For me, again, what I don't know if to say fascinating, but anyway, there's a connection here between growth and varieties over the group.
Zlil, maybe before we proceed, there's a question of Zoe's in the chat that may be relevant at this point before you get into the sketches of the proof. If you want to have a quick look and see if you want to answer it now or in the end.
No, I don't. Okay, I don't know to answer this question. I don't know anything about computing this invariant or whatever. I don't know anything. There are many questions that this raises, I think. I don't know if I'll get to post some of them. I have slides with that, but no, I don't, about computability, I don't know. I really don't. I don't know anything. I don't even know, even for free group, what will be the first. What's the real number which correspond to the first limit ordinal? I don't know. I don't know anything except what is one. That's all. I really don't know anything. There are many questions here. Okay. Yeah, it's mostly raised question. Okay, so yeah, let me just explain why this is connected to varieties over the group. See, in order to prove that, yeah, somehow, okay, in order to prove that, well, I'm puzzled whether to talk about the argument or to just go to maybe I'll go to some other result. If there is time, I'll go back to the, okay, to sketches of the argument, because anyway, I'm not going to get the full argument. So sorry, because this has generalizations. Just in a matter of time. Okay, these are all has to do with the argument. Yeah, okay. Okay, even see this for me was quite appealing that okay, we basically get a set which is well ordered and has its ordinal, it has limit ordinals, as somehow the limit ordinals are exactly correspond to limit groups, which are limit groups over the group, which are the coordinate group of varieties, of irreducible varieties over the hyperbolic group in question. Even there syntactically, I mean, when I define limit groups, I never thought that it has any connection with ordinals, but somehow limit ordinals are give precisely the growth of limit groups, and this is also a way to somehow naturally close the set of growth by adding the growth of limit groups over the group. Okay, of coordinate groups over coordinate groups of varieties over this group. Okay, but let me. Okay, I want to go over some more results, and yeah, I don't know if I'll have time now to go about the argument. I planned it, but okay. So okay, so one can go further, and in a sense, this is even more surprising, I think, because hyperbolic group, one can say, okay, we know quite a bit on their structure. Okay, of course, one can argue what quite a bit is, but if we consider all subgroups or finitely generated subgroup of hyperbolic group, this is already quite a wild object, quite a wild set. There is a well-known example of Reeves, which is very short, it's just 2 pages, but it's very clever, from 1981. What Reeves showed is the following: that if you take any finitely presented group, so any finitely presented group, there will be a hyperbolic group, even better than that, small constellation group. So there will be a hyperbolic group, so that this finitely presented group is the quotient group, and the kernel will be a group generated by 2 elements. So you see, it means that for any finitely generated subgroup of this finitely presented group, we get some finitely generated subgroup of the hyperbolic group. So it looks almost as bad as subgroups of finitely presented groups. It's not exactly true, but many pathologies afterwards were built after Reeves using his construction. And of course, generalization of this construction also for other families of groups. Like Martin Brightson has a whole sequence of them, and also others, Danny Weiss. quite a few others. Okay, so what we are going to do now, okay, in a sense, we cannot say much about the collection of all finitely generated subgroups of hyperbolic groups, but we look now at the set of growth. Okay, we denote this by theta. It's again a countable subset of the reals. We look at all subgroups of the hyperbolic group, all finitely generated subgroups, let's say, all finitely generated subgroups of the hyperbolic group, and all their generating sets. Okay, so all of them together, not one separately, but all of them together. Okay, so again, it's all the growth of finitely generated subgroups with respect to all their possible finite generating set. If you want, this is more or less looking at all finite tuples of the group and the group that they generate. And somehow, rather surprisingly, the same theorem is true. So this set is also a well-ordered set. And the same theorems about ordinals are also true here. So, okay, in general, it's greater or equal omega 0 to omega 0. And if we know the result of Lauder, which he doesn't know in general, but for hyperbolic groups, but for groups that he knows it, for what we call whole dimension of varieties over the group, then actually the ordinal is still omega 0 to omega 0, even though this is a much bigger set. And here, the finiteness that Udi asked about before is still valid here. So every real number can be the rate of growth of at most finitely many pairs like that. Pair meaning a subgroup with a generating set, and now we need to identify them. The equivalence class is of course up to isomorphism. Okay, so so a group can be a subgroup of hyperbolic groups in many ways, but if we pick the same group up to isomorphism, and this isomorphism take one generating set to another, we identify that. And up to this natural equivalence relation, because this doesn't change the growth, we get the same finiteness as before. And this is rather surprising because it's not clear why in general, for example, if you take 3 generated subgroups of a given hyperbolic group, there will be infinitely many of them. And it's not clear why this finiteness is actually true, why they avoid one another in some sense, but it's still true. Okay, this is the same. This is as I said, the result about the ordinal. We get just the same result as before. And now I want to go to another generalization. And somehow, for me, conceptually, this is in a way this is the most surprising because this is the wildest set that we look at. Although, of course, for popularizing this result. This is not the best idea because people, at least in group theory, usually don't look that much or about semigroups. But semigroups, see, if we think of all the subgroups of hyperbolic group, this is already wild. If you look at sub-semigroups, this is completely just even sub-semigroups of a free semigroup. You know, all subgroups of free groups are always free. In particular, the finitely generated ones. If you fix a finitely generated semigroup and you look at their finitely generated sub-semigroups, they need not even be, they're of course not free in general, but they need not be even finitely presented. So this is a completely wild object. And okay, but we still look, we fix the hyperbolic group, and we look at all the sub-semigroups inside, finitely generated sub-semigroups inside, with respect to all their generating sets. And still the result is the same. I should say in the paper we prove that this set is well ordered with the same bounds on the ordinal as before. And we didn't prove finiteness in the paper, but I think even the finiteness is true. But strictly speaking, it is not included in the paper. But essentially the same result as for subgroups or for generating set of the group hold for semigroups. And I said that this was appealing for me because, you know, one thing that I learned, and you know, this in some sense this I think distinguished logicians from other mathematicians, that mathematicians usually are not used to think in a way that you can change the signature of the object that you work with, and still just properties of the theory will guarantee that you know, you can freely move from one signature to another. Usually mathematicians are not used to think in this way. And this is very special to logician. Of course, it's a very powerful tool. And this was appealing for me because the reason that one can move here from groups to semigroups is because I generalize all my work about varieties from groups, from free groups to free semigroups. So, okay, here it's hyperbolic, but that doesn't matter. Because of this generalization, one can also, we change here the signature also. We move from group to semigroup, but because all the work was ready, then the generalization is, well, there are some technicalities, but it's pretty straightforward. And I think, you know, we still don't understand completely how varieties over, say, free associative algebras look like. Certainly still considerably more difficult than semigroup. But if we have analogous theorems for associative algebras, then this type of theorems of growth will be also valid there. Okay, but okay, we're still far away from that. But this will allow again to move from one algebraic object to another relatively easily if these methods are ready. Okay, this is not the type of how to say, of characteristic of a theory that logicians are used to work with, but these are here is properties of varieties that somehow go from one algebraic object to another, even though we change the signature.
Zlil,
Yes?
you said properties of varieties. How do you see a property of a variety here?
What do you mean, of a semigroup? Oh, why is this connected?
Variety of semigroups. Sorry, no, I understand. Okay, sorry. I thought you meant a variety over the group. Okay.
No, it's a variety over a semigroup. But the thing is that varieties over semigroups have many similar properties as varieties over groups.
No. So you are saying this. So variety means an equation, right? The set of solutions to some equation. So
right,
which equation it appears here?
But it's equations over the semigroup.
So the implicit equations that lower the growth rate from something bigger?
No. It's now you ask what equations one should look at.
Yeah.
Okay, for this I need to go back and go to the sketch of the argument. I wanted to, because you see, now I didn't give the feeling why varieties come into the picture here, and in particular I need notoriety, which is not at all obvious, but it's true. For hyperbolic groups, even though they're not linear or anything like this, but notoriety will hold, or holds. Sorry. I need to explain how varieties. It's not clear why it comes into the picture. For this, I had to say at least something about the sketch of the argument. Okay. I'm sorry about that. Let me just see. Yeah, this is okay. The problem is that I'm almost exhausted my time. Okay, I'll say something about, at least it will answer, okay, with this question. Wow, what happened to me now? Okay. I'll just start with the beginning of the, I'm sorry about, of this argument. Okay, so I'll just talk about, okay, I hope this will, at least to give a hint why varieties come in. So this is again, it's a sketch of the argument as why the ordinal is well ordered. Okay, and now about the whole group, but one can translate the argument then to study subgroups and to study semigroups or sub-semigroups. Okay, so the first thing that one observer, this is again a result of Rodjantseva and Lisenov, that if we fix a growth, or in other words, there is a lower bound on the growth in terms of the number of generators. So when the number of generators in the generating set grows, the growth grow as a function of n, say something like square root of n or something. It doesn't really matter, but it grows to infinity. Okay, so if we want to show that there's no decreasing subsequence that there's no convergent decreasing subsequence. So we can assume that the number of generators is bounded, and after passing to a subsequence, we can assume that it is constant. Now, what we do is we view any generating set as a homomorphism from a fixed free group into the hyperbolic group, into the hyperbolic group. In here, this will be a generating set. In the other cases, it's not. Okay, but anyway, it's a homomorphism from a free group on into the hyperbolic group, and this sequence contains a convergent sequence. That's a standard compactness argument. It means that for every element in the group, there will exist an index depending on the, after we pass to subsequence, there exists some index, so that for any element, for any index above this index, either the element is always mapped to 1 or it's always mapped to something which is non-trivial. Then we look, I'm sorry, I'm doing it a little bit quick. We look at the elements that are trivially stable, and then we look at, this is a normal subgroup, and then we look at the quotient of the free group of the source modulo the stable kernel. This is called a limit group over the hyperbolic group, which is the target. It's a quotient of the free group, but it's called a limit group over the hyperbolic group.
Mm-hmm.
Okay, and now we use noetherianity. And what noetherianity will mean that in this setup, it means that, you see, we have this sequence of homomorphism from the free group into the hyperbolic group, taking the free basis to the generating sets. And this is this limit group that we had before. Okay, and noetherianity will mean, okay, I'm not going to explain it now, but noetherianity will mean that for large n, this homomorphism Gn factors as a fixed quotient map from the free group to the limit group into the hyperbolic group, taking the fixed generating set of the limit group into the changing generating sets of that appear in the sequence of the subsequence of the hyperbolic group. Now, all these guys are quotient of the limit group. Okay, so the growth rate is actually it's bounded above by the limit group. But what we argue, and this requires some combinatorial argument, which I'm not going to get into now, that on one hand, the growth rate of all these guys are bounded above by the growth of the limit group. But on the other hand, we can show, okay, this is a limit group, but it turns out that the limit of the growth is equal to the growth of the limit. Okay, somehow change of order of limits, which is true here. It's not true in general, but it's true here, and true in many other families of groups. Okay, that and this is impossible if we have this change of limits. If we know that the limit of growth is equal to the growth of the limit, well, this cannot be a convergent decreasing sequence, because this decreasing sequence is bounded from above by the growth of this thing. It cannot converge into it. Okay, so this will be a contradiction. So what we use actually from the theory of limit groups is basically, at least here, not for the ordinals we need more, but here we use this noetherianity, which is true for hyperbolic groups, and again, it's true. It's known also for other classes of groups, not for very many. Usually, it's a very difficult question, and this is noetherianity for varieties. That's as you are used to from, I don't know, complex algebraic geometry. Mm-hmm. What we need for the ordinal is something stronger, not just noetherianity, but we need to know that if we start with an irreducible variety and we look at the sequence of varieties, that irreducible varieties that are properly contained into it, a sequence, then we need a uniform bound on the length of these sequences. Okay, noetherianity just says that every such sequence terminates, but we need a uniform bound on the length of this. We don't need only descending principle, but actually a uniform bound. Okay, I will stop here.
Thank you very much for a very beautiful talk. Are there any questions?
So yeah, it's a very exciting, beautiful talk. All these results are for a fixed hyperbolic group, right? I mean, suppose you have two hyperbolic groups that have the same ordinal and the same real numbers. Can you say something about them?
No, right. This is actually, okay. First of all, we conjecture that the ordinal for all hyperbolic groups, the ordinal of the whole set of groups is always omega 0 to omega 0. Because we cannot prove it now, but we conjecture that this is the case. But indeed, the set itself will vary from one group to another. That's not difficult to see that it's not the same for different groups. Just the ordinal of the whole set is the same. Actually, it appears is one of the questions that I had at the end in one of the slides. Just the question that you ask now. There's a list of problems there, and this is one of them. We don't know what if you know the set, we don't know what it says about the algebraic structure of the group. This is an interesting question, and yeah, I mean, okay, there are many things that that one can ask about these things, and practically nothing is known.
Other questions? Okay, so let's thanks Zlil again for a very beautiful talk indeed, and we'll reconvene in 10 minutes.
Actually, Asaf, is it possible to ask that all the slides will be posted as well as the, I mean, at the moment the videos are posted, but people's slides are not posted.
I guess that we should ask Sylvain about this because
I can talk with Shane and Brian about it. I'll do that and tell
send my
you.
slides. There's no problem.
Yeah, send me your slides and I'll try to see what we can do with it.
Okay, but can you? I'm not sure I have your address, so this is.
Send it to Asaf.
so send it to me. I mean, no problem.
Okay. I'll send it to Asaf. All right, no problem.
Okay, so we'll meet at 7. I mean, Israel time, 9 minutes from now.
Okay. Get out of that.